Good day, everyone. Allow me to introduce myself. I am Gerald Agustin, a registered chemical engineer and an advocate for environmental sustainability. Well, some of us here maybe are fond of going to beaches, swimming, and enjoying the saline water near the coasts. But have you ever wondered how these seawaters be of more benefit to us? Well, let's find out. This presentation focuses on desalination, particularly on its breakthroughs and its future perspectives. So I will be talking about first, the problem statement, second, the introduction of the main topic, third, are the current trends and advances, fourth, the future directions and also the challenges, and fifth, the conclusions. So stick with me and let's dive into these conversations. Water is one of the basic necessities for the existence of life here on Earth. With the increasing world population and climate change that is happening around us, the scarcity of freshwater resources has become a critical issue. According to the IPCC, or the Intergovernmental Panel on climate change may likely to cause droughts to continue to get worse, that the possibility of droughts will increase fivefold by 2050. As we may know, 96.5% of Earth's water is ocean, with only 2.5% is fresh water. And about 70% of Earth's fresh water is found in ice caps, glaciers, and snow. So definitely, finding an alternative sustainable solution is a must to solve or to address these issues. Accepting this reality, unconventional water technology, primarily seawater desalination, has been declared to support the United Nations Sustainable Development Goals, particularly the Goal 6, which is about ensuring availability and sustainable management of water resources and sanitation for all. In this light, desalination is a reliable solution to the shortage of potable water that is happening across the globe. Seawater, which is highly saline, has a salt concentration of 35 grams per liter, which is not suitable for drinking purposes, and let's say a wide array of functions or uses. So the demand or the increase on the demand of potable water and the shortage of surface water led to the development of these desalination technologies to obtain fresh water from seawater or can also be brackish water, which can also be a water source. Okay. Denotatively, desalination describes any process that removes excess salt and other minerals from water. A desalination plant normally includes first the intake, which is composed of pumps and pipes to take water from the source. Again, sources could be seawater or brackish water. And then the pre-treatment processes. Say we have conventional pretreatment processes, and we also do have the more modern technologies for pretreatment processes. So for the conventional type, we do have coagulation, flocculation, and such. And for the modern type, we have now an emerging technology on membrane-based technology, which I will be further discussing on the latter part of this presentation. But all these pre-treatment processes uh, aim to remove solid components, and also we'll be adding some chemicals um, in order for us to hinder the salt precipitation. Next is the particular desalination technology, say for example an RO or reverse osmosis technology, where fresh water is extracted from salt water. And the last process is the post-treatment. This is basically to correct pH by adding selected salts to meet the requirements of the final uses. Say, for example, our ultimate goal is to have or to obtain drinking water. So we'll be having to adjust the pH as to how we want our resulting water to how are we going to use the resulting water? Well, historically, the idea behind the desalination process was introduced by the Royal Navy in the 18th century, with the purpose of increasing navigational autonomy without storing more water on the ships. It was then in 1907 that a Dutch company installed the first desalination plant in the Arabian Gulf countries, particularly in the city of Jeddah. Soon after, in 1953, other desalination plants were installed in Qatar and Kuwait. It was then in 1952 that the United States of America took its steps on adopting this desalination technology as the U.S. Congress passed the Saline Act and established the Office of Saline Water. It became common in 1960s where desalination plants are based on thermal processes. The first membrane reverse osmosis technology was realized in 1959, whereas the first pilot plant was installed in 1965 with a capacity of 19 cubic meter per day. So the first desalination plant based on RO or reverse osmosis technology was installed in 1977 at the United States of America with a capacity of 11,350 cubic meter per day. So these great technological progress occurred in the process of reverse osmosis owing to the development on the increase of membrane lifespan and the efficiency when it comes to energy consumption. So nowadays, reverse osmosis or RO is considered to be the most widely used or most commercialized desalination technology around the world. Soon after the advancement of desalination technology in the Gulf countries and in the United States, um, the Asia Pacific region has already took its steps also in adopting this technology. It is said that the Asia Pacific desalination market grew further in 2017 to 2018 as the Chinese desalination sector joined the Gulf desalination sector. And based on their progress report, well, they are aiming to or they intend to build many new plants before 2025. So here are the classifications of desalination technologies. We have evaporation and condensation, filtration, and crystallization. So these are the major classifications, okay? But first, let's focus on the evaporation and condensation. So it is said that evaporation and condensation desalination technologies are the first desalination technologies being installed or being introduced and used for civil freshwater production. So we have two types, the mechanical process based and thermal process based. Under thermal process, the most common ones are the multi-effect distillation, multi-stage flash, thermal vapor compression or TVC, while others are considered as emerging technologies, which are the solar steel distillation, humidification, the humidification desalination technology, and the SC or the solar chimney. Um, the mechanical process is the mechanical vapor compression, which is based on the production of fresh water using evaporation and condensation of seawater. Well, generally, this evaporation and condensation technology is based on the idea. Well, the idea is to supply thermal energy to seawater, producing a vapor, and then condense it. Okay. Now let's move forward to filtration process. So here are the common filtration processes. The first one is reverse osmosis. While in this context, reverse osmosis is considered to be the most widely used desalination technology. And then we have other emerging technology, which are the forward osmosis, nanofiltration, ion exchange resin, membrane distillation, electrodialysis, and the CDI, or the capacitive deionization technology. So these are labeled as emerging technology um, because these are still under investigation and um, it is based on its capability to be commercialized or industrialized. Okay, and then the last technologies would be under crystallization, which are secondary refrigerant freezing, and hydration, which are considered to be uncommon desalination technologies. Now, I would like to share with you this desalination situationer, focusing on the statistics on this desalination technology and yeah, its current status. According to a recent report published by the International Desalination Association or IDA, as of February 2020, almost 21,000 desalination plants are either constructed or contracted to be constructed, and the global installed and cumulative freshwater production stood at 97.2 million cubic meter per day and 114.9 million cubic meter per day, respectively. According to another report published by the IDA and Global Water Intelligence or GWI in 2019, the seawater desalination market experienced its most dynamic year since the late 2000s. Based on facts released by both IDA and IWA, at present, about 1% of the world's freshwater comes from desalination methods, where more than 300 million people, or about 4% of the global population, rely fully or partially on this source to fulfill their daily water needs. Now, I would like to highlight reverse osmosis or RO as the leading desalination technology worldwide. Reverse osmosis is a cross-flow filtration method whereby contaminants are caught within the filter itself. In reverse osmosis, feed water is demineralized or deionized by applying pressure to push it through a semi-permeable membrane, leaving the salt on the other side. So here in this figure is an overall desalination process based on reverse osmosis, so which is um, divided into three major parts. First is the pre-treatment, and then the reverse osmosis operation proper, and then the post-treatment. As for the pre-treatment, we do have two types, the conventional and the more modern part, which is the membrane-based pre-treatment process. So focusing first on the conventional pre-treatment process, it starts with coagulation and flocculation to remove I mean, well, in coagulation and flocculation, we may use chemicals such as ferric chloride. It is followed by granular filtration to remove coarse solids, let's say, for example, an algae, and then followed by cartridge filtration to remove smaller solid particles such as fine sand. Now, for the membrane-based pretreatment, it starts with coarse strainer with pore sizes of greater than 5 micrometer, and then followed by the microfiltration, which has pore sizes of um, a zero point 0.1 and 5 micrometer, and lastly, ultrafiltration or UF, which has pore sizes of 10 to 100 nanometers. So, in line with these conventional pretreatment processes and membrane-based pretreatment processes, they both use chemicals such as bisulfite and sulfuric acid and what else? Well, generally anti-scalants such as polyacrylates, which are necessary for the pretreatment process. And so the pre-treated water will then flow through the feed channel at high pressure. Typically, for the reverse osmosis operation, pressure is between 55 to 70 bars, so that the water could pass through the pores of the semi-permeable membrane contained in a membrane module. So that's it, the reverse osmosis operation. And then for the post-treatment process, typically this contains a minerals enrichment unit whereby ions such as magnesium and calcium are added to the permeate water. So we can also add disinfection process This happens when chlorine is added to water to suppress the growth of microorganisms during water distribution. And then the waste brine from the reverse osmosis operation serves as an effluent, which will then be sent back into the ocean.
Reverse osmosis offers significant advantages over conventional desalination technologies, including high production capacity, lower operating costs, and smaller internals, resulting in more compact equipment. It is providing reliably clean, potable water for millions of people whose lives depend on it. The RO process can remove up to 99% of the dissolved particles such as salts, colloids, organics, and bacteria from the feed water. These RO membranes reject these contaminants based on their sizes and weights, where typically any contaminant with a molecular weight of greater than 200 atomic mass per unit is expected to be rejected by the RO system. In terms of efficiency, the permeate or the fresh water produced using RO method varies between 30% to 60% of the feed water, depending on the membrane technology used and other factors such as the osmotic pressure that is being applied. Well, overall, reverse osmosis is a highly scalable process suitable for a range of systems, including smaller plants to systems with a production capacity as large as 600,000 cubic meter per day. Now, here are the disadvantages. The use and cost of reverse osmosis have been a trade-off between low operational cost in terms of energy versus high associated capital cost, that is, installation and replacement of membranes. The recent technological developments are helping to increase the membrane life along better feed water pre-treatment methods and understanding of how to operate and handle the membranes, also helping to reduce the maintenance costs of the reverse osmosis facilities. This is the reason more and more desalination plants are shifting towards the use of membrane-based processes. For example, in the year 2020, reverse osmosis desalination plants account to 84% of the total number of global operation of the desalination plants, providing 65.5 million cubic meter per day of fresh water. It is also worth noting that this reverse osmosis is a very energy demanding process, leading to high GHG emissions or greenhouse gas emissions. The use of electrical energy also means that this reverse osmosis technology is inaccessible or too expensive in many regions with high water demand. Other key limitations include membrane fouling and limited water recovery, leading to large amounts of waste brine. One of the major challenges of the reverse osmosis technology is what we call membrane fouling. Solute buildup at the surface of the membrane, known as the concentration polarization, reduces the pressure gradient across the membrane, reducing the flux and increasing fouling and scaling. As defined, fouling is the deposition of organics, inorganics, or biological material on the membrane, and scaling is the precipitation of inorganic material onto the membrane surface. Biofouling can be controlled by the addition of chlorine during pretreatment process, which also mitigates the growth of the microorganisms. Also, one of the major foulants or cause of fouling is or are the microplastics that are increasingly found in the oceans. So these are membrane foulants during reverse osmosis proper and the ultrafiltration pretreatment process if the particle size is above 100 nanometer. Also, one of the drawbacks of this reverse osmosis technology is about its energy consumption. It is said that this RO technology is energy intensive. 71% of the total desalination electricity is consumed by the RO process, 11% by pretreatment, and the rest is used for seawater collection, distribution, and ancillary facilities. But the consumption of energy of this RO process have decreased significantly over the past decades owing to the improvements on its process. However, since there is a shift on the usage of pretreatment process, so from conventional processes are coagulation, flocculation, and such. So now we're shifting towards the use of membrane-based pretreatment processes such as microfiltration and ultrafiltration. And actually, these actually have higher energy consumption. So now there are these studies on the utilization of renewable energy for renewable electricity to supply our reverse osmosis process. So examples of which are the use of wind energy and solar energy. Particularly, this is a desalination plant in Oman that utilizes solar-powered grids to contribute to the demand on electricity for the RO process. From a drawback, it's another drawback, which is now on waste brine. Elimination of RO brine is one of the key challenges in preventing water contamination from desalination. The water recovery in most seawater RO plants is limited to between 30% and 60% of the feed water, and beyond this range, the required energy for separation increases exponentially. So this dependency between water recovery and energy means that zero liquid discharge systems, which recover 100% of pure water, are hard to achieve with RO alone, and thus waste brine is produced. There is this study by Jones et al. In 2019 that estimated that the actual global brine production was about 50% higher than previous estimates. This means that the water recovery of RO plants sits at the lower range of the previously mentioned 30 to 60% recovery. Thus, RO plants produce around 2 cubic meter of concentrated brine for every 1 cubic meter of treated water. And unfortunately, or sad to say, globally, over 90% of seawater plants discharge brine directly into open water bodies. So now there is an increased public awareness and a growing number of studies demonstrating the adverse impacts of brine on marine life due to increased salinity. These studies have led to further restrictions on the disposal and treatment of brine, which is, expected to draw motivations for further developments of alternative methods. The brine also contains dissolved chemical products from pretreatment, including iron chloride, sodium hypochlorite, and sodium bisulfite. And even at low concentrations, these chemicals may impact negatively on the marine ecosystem or the marine life. So there are recommendations for responsible management of the brine impacts, which include modeling the brine plume to understand the diffusion rates. We also have longer term monitoring of population and distribution of nearby marine ecosystems and frequent water sampling checks in the brine discharge area. As mentioned, the key to mitigating these problems or challenges on waste brine is the proper brine management. Along with posing various environmental challenges, the desalination sector has great potential to convert brine into some valuable resources as a byproduct. Based on its chemical composition, researchers are focusing on this advantage, which can be beneficial economically and ecologically, especially considering the dramatic future growth of the desalination sector. It is worth mentioning that some of the minerals in seawater are rare and expensive to mine on land, thus extracting these minerals from brine is possible, but the high extraction cost restricts its commercialization. And that's another story to tell. But currently, desalination plants spend money buying sodium hydroxide, for example, but it would bring a great benefit if they could extract it in situ at the plant, and that is through the reuse or proper management of the waste brine. Along with sodium hydroxide, another important chemical used for industrial processes is the hydrochloric acid, which can also easily be produced on site. The locally produced hydrochloric acid can play a critical role during the desalination process as it is commonly used to clean the parts of the desalination plant. So these are some of the um, effective and possible actions to mitigate these challenges on waste brine. Climate change, once a negligible concern, has now become the greatest challenge of the current era. Considering the climate situation of the planet, a group of scientists has warned that Earth's vital signs are worsening rapidly, and as a result of these changes, water reserves already under pressure will be the first victim of these climate changes. Among all the essential factors for restoring the ecosystem, one important component that can effectively address the climate issue is water. That is, how we utilize and produce it. A drought has generally been defined as a prolonged period of abnormally low rainfall, but considering the situation over the past few years, such rain-free period seems to be the new normal, as many regions persistently experience these conditions. The year 2021 might be the year in which scientists and climate experts highlighted these climate issues as never before. Reports and articles linked with extreme heat waves, droughts, and climate change remain common in headlines globally today. Earth sizzled in July 2021 as it measured the hottest month in 142 years of record keeping, while more alarming is that such record rises in temperature are occurring frequently. As a result of this phenomenon, the language of climate is evolving from change to catastrophe, which ultimately will result in some regions being parched while others are being soaked. Over and above this, droughts are drying up rivers and reservoirs that are vital for the production of zero emissions hydropower, the world's top source of clean energy, which constitutes about 16% of the electricity generated in the world. In all the regions facing rapid depletion of freshwater reservoir, the water crisis may quickly turn into a power crisis, in which all these effects are directly linked with water scarcity, as every 1 degree Celsius increase in global warming is expected to lead to the loss of at least 20% of the renewable water resources of 7% of the world population. In contrast, traditional desalination processes increase greenhouse gas emissions or GHG emissions, as you can see here in this graph, because they largely depend on fossil fuels. Well, in some cases, they use heavy fuel oil, which creates carbon dioxide emissions. In general, producing 1,000 cubic meter of water or 1 million liters a day through thermal desalination requires about 10,000 tons of fossil fuel annually. When the carbon footprint of seawater desalination is calculated, even using an energy efficient RO or reverse osmosis technology, desalinate, desalinating each 1,000 cubic meter leads to the potential release of zero point 0.4 to 6.7 tons of carbon dioxide, depending on the plant size and other operational procedures. According to the IEA's World Energy Outlook report in 2016, the energy consumed by the desalination sector only in the UAE equivalent to more than 13 million tons of oil. Unfortunately, we all pay for the price of such gigantic energy consumption. The global carbon dioxide emissions from the desalination plants powered through fossil fuels were estimated at 76 million tons in 2020. Furthermore, if the operations continue with same procedures, then the figure can reach 218 million tons of carbon dioxide by 2040, as shown in this graph. If we combine all the effects of desalination, the amount of released greenhouse gases such as carbon dioxide, methane, and nitrous oxide rise higher than the annual average over the past 10 years. Carbon dioxide levels will reach 413.2 ppm in the atmosphere in 2020, which is 149% of the pre-industrial level. So imagine the impacts of the desalination of this desalination technology. Consequently, this changes fuel climate issues, ultimately destabilizing the existing limited freshwater resources as the wet regions of the world get wetter and the dry areas get drier. And all these processes are happening faster than previously thought. A recent report on Global Carbon Budget 2021 revealed that at current levels of emissions, there is a 50% chance that the 1.5 degrees Celsius rise expected by the end of this century will be locked in by 2033. And all these facts show that the factors like climate changes, existing freshwater reservoir, and desalination processes are directly linked and greatly affect each other as depicted in this figure. Whenever we talk about the potential drawbacks of desalination, mostly environmental issues are raised. However, some serious health issues are also linked with the water produced using this process. Unlike water found in natural resources, water produced through this procedure is low in minerals and slightly acidic. The presence, absence, or even imbalance occurrence of these beneficial ions can affect human health when continuously used over long periods. We may know that seawater is rich in calcium, sodium, and chloride, but low in other essential ions such as zinc, copper, and manganese. As we may also know, ocean is large and wide, that it may contain many toxic substances, microorganisms, and say, solid particles, such as raw and refined petroleum elements. Along with these materials, there could also be various byproducts of the chemicals used in desalination that can also pass into the produced water to affect the person who drinks it. Although we do have the post-treatment processes that are being applied to desalinated water to stabilize some of these ions, yet providing balanced dietary components targeting a varied population such as children, aged people, and pregnant women is a complex task. Due to the continuously increasing role of desalination to quench our thirst, the the World Health Organization has already provided guidelines that declare that regular consumption of reverse osmosis water can create some health side effects. As per researches, drinking RO desalinated water can cause more harm and faster bodily effects than most of the contaminants found in tap water. The major reason is that the desalinated water lacks imbalanced minerals that are vital for human health. For example, usually 92% to 99% of the minerals such as calcium, magnesium, fluoride, and iodine are removed along with impurities. And such health issues have also been proven through specific and targeted studies. And so, to ensure the availability of quality domestic water parallel to such mitigation or such specific efforts, the world also needs a global policy and standards to evaluate if these mitigations or such specific actions are really are really can be applied or is really effective.
So, with thousands of reverse osmosis desalination plants currently operating and with no current plans yet for deployment of large-scale plants utilizing alternative methods, meaning methods aside from RO, it could be a long time before the desalination industry to replace RO. Therefore, hybrid systems can be an excellent opportunity to test, further develop, and grow confidence um, in these new systems. Here is a comparison of standalone and hybrid systems in terms of five criteria. We have low energy consumption, low water costs, high water recovery, ease of pretreatment, and ease of integrating renewable energy. So the comparison is based on a scale of 0 to 1, where values closer to 1 or unity is preferred, and all the criteria are considered to be of equal importance. So here, on this basis, the ROFO or reverse osmosis forward osmosis hybrid system is considered to be the best option as the only alternative with two of the criteria equal to unity. So that is low energy consumption and ease of pretreatment. It also has the second lowest water costs. Mhm. And to n- next to ROFO is the ROMD or the reverse osmosis membrane distillation hybrid system with the highest water recovery.
And then MCDI, or the membrane capacitive deionization standalone technology, is the worst option among the standalone technologies. And it is interesting to note that the hybrid systems tend to perform overall better than the standalone technologies. However, these comparisons should be treated with caution due to a lack of data related to commercial applications of the emerging technologies. And some criteria may be considered more important than others, particularly the energy consumption and the costs. And it should be kept in mind that reverse osmosis is the only option that is scalable and currently optimized. So if these emerging technologies could be deployed commercially, this would also benefit from the economies of scale, and their performance would definitely improve. I would also like to highlight one of the emerging technologies, which is the CDI, or capacitive deionization. Although CDI was already introduced in 1960s, it's the lack of large-scale energy-efficient plant utilizing CDI that reflects its status as an emerging technology. CDI, which is based on the electrosorption of ions by porous electrodes, is an emerging technology suitable for brackish water desalination. Using the CDI process, salt minerals are removed by applying an electrical potential difference to saline water over two electrodes. So although based on current developments, CDI cannot compete with the commercialized reverse osmosis based technology on both energy consumption and capital costs. But it can be good as a post-treatment process. So there are these experiments done that uh, which found out that permeate produced after the first phase with a seawater reverse osmosis technology plant treated by CDI instead of applying the second pass of RO system was drinkable or potable. So, and well, this also is my line of interest now for my thesis topic. So let's see how are we gonna unravel or have new findings on this technology. The Earth's water resources are in a sad state after decades of mismanagement, while extreme environmental changes are hastening their decline. Surely the world needs to, diversify its freshwater sources, and for this, we need to have more tools in our toolkit. In the current scenario, desalination is considered a sustainable solution to water scarcity due to its capability for using unusable and vastly available seawater or brackish water. But there are these significant issues such as energy requirements and severe impacts on the environment, which are actually major hurdles currently preventing its success. Hence, more research is required, particularly to address the following concerns. One, the appropriate location and the consideration of the environmental impacts in the pre-design phase of the plant can make the process to occur without leaving significant harm to the surrounding environment, while these scientific approaches, especially those utilizing recent technologies, can be really helpful. Two, focusing the growth of desalination, not only we need energy efficient desalination procedures, but also we need these innovative solutions for sustainable energy production. So for this purpose, what we can do is to enhance the energy recovery method, which can be really vital to achieve this goal. Number three, new desalination methods that utilize optimized chemicals and pretreatment technologies can also help to achieve energy efficiency. We can go actually one step further and develop alternative green chemicals to replace the rest of the essential chemicals to mitigate their negative impacts. 4. The transition to low carbon desalination, while a complex and time consuming process, cannot be overlooked, especially in the face of the climbing global agenda for reaching these this ambitious, let's say ambitious decarbonization targets. Five, many prominent efforts have been witnessed recently to make the desalination a sustainable process. However, um, I think the actual benefit of all such efforts can be felt only once they will be able to produce the fresh water at large scale. Now, the question is seawater desalination the solution or the answer? Well, based on the facts that I have mentioned or that I have laid, one can conclude that seawater desalination is the merely choice for arid regions. When we say arid, these are places having little or no rain or too dry regions in the absence of a freshwater reservoir. Moreover, this facility or this desalination facility is naturally appealing to those coastal areas wherein currently about 40% of the world's population is found within 100 kilometer of a coast. Now, currently at a limited scale, other options such as air to water and cloud seeding could also become a reality in the future, but these technologies will not come at will not come sooner at a large scale. So considering all these factors, seawater desalination offers a logical and sustainable solution, and the long-term management of growing water demands in denser zones of population. That's it for my report. This has been Chanel Agustin. Thank you so much for listening and watching. May you enjoy the rest of the day. Bye.